It began as a ghost, a silent pilgrim wandering the dark for millions, perhaps billions of years. Imagine a traveller born in the frost and shadow of a star system we will never see, a place unimaginably far from our own. This traveller is ancient, frozen and utterly alone. It is a piece of a different home, a fragment of a world that never was, kicked out of its own cradle by the pull of giant planets or the close pass of a neighbouring star. It has drifted through the interstellar void, the vast empty ocean between the stars at a speed we can barely comprehend, a time capsule preserving the secrets of its birth. And then in July of 2025 it swam into our net, our telescopes, specifically the asteroid. Terrestrial Impact Last Alert System, or ATLAS, sweeping the skies for danger, caught a faint smudge of light where no smudge should be. At first it was just another data point, but as astronomers watched it night after night, a strange and thrilling story began to take shape. They tracked its path, tracing its journey through our solar system. The math was undeniable. This object was not one of ours. Its path was a perfect hyperbolic orbit. In simple terms, this means it was moving too fast to be caught by our sun. It wasn't looping around like our planets and comets do, bound by gravity. It was a visitor on a one-way ticket. It had fallen in from the deep darkness of interstellar space, and after swinging around our sun, it would be flung right back out, never to return. This was 3 Atlas, the third interstellar object ever detected. We have had visitors before, and each one taught us something different. In 2017, we met Oumuamua the first. It was a complete mystery. It looked like a strange rocky cigar, and bafflingly it had no tail. It left us with more questions than answers, a puzzle that still haunts astronomers. Then in 2019 came Borisov. Borisov was a relief. It looked and acted just like one of our comets. It had a big beautiful tail made of water ice, just like the comets from our own backyard. Borisov told us that other solar systems were probably built a lot like ours, but 3I Atlas is different. It's not a strange silent rock like Oumuamua, and it's not comfortingly normal like Borisov. It's a brand new kind of mystery one that is challenging our fundamental models of how solar systems are built. The weirdness began almost immediately. 3I Atlas started to grow a tail to get active. As astronomers say, while it was still incredibly far from the Sun, out past the orbit of Saturn. This was wrong. It was happening in a place that is profoundly cold, far too cold for water ice, the main ingredient of our comets, to turn into gas. A comet's tail is formed when the Sun's heat boils its ices like a kettle on a stove. But 3I Atlas was boiling while it was still in the deep freeze. This anomaly told us one thing immediately: that this object is not made of the same stuff as our comets. It must be made of exotic ices, materials that have a much, much lower freezing point. Imagine a block of frozen nitrogen or solid carbon monoxide, or the dry ice of carbon dioxide. These super frozen gases will turn to vapour even in the faint weak sunlight of the outer solar system. This visitor, it seemed, was not a dirty snowball, but perhaps a dry ice ball or something even stranger. And the tail it created was just as bizarre. It was described as thin, faint and ghostly. Our computers running models of how gas and dust should behave couldn't quite replicate it. The physics seemed skewed. The way the dust was streaming from its surface was not following the rules we had written. We needed a better look. We turned our most powerful eye, the James Webb Space Telescope, to stare at the visitor. Webb sees the universe in infrared light, the language of heat and chemistry. It can tell us not just that the comet is active, but what it is made of. The results that came back were stunning. The gas pouring off 3I Atlas was dominated overwhelmingly by carbon dioxide. In our solar system, water is king. Our comets are almost all water. Carbon dioxide is just a minor ingredient, a little bit of fizz, but in 3I Atlas the recipe was flipped. This was a carbon dioxide comet. This single chemical signature was a revolution. It meant that wherever 3I Atlas was born, the ingredients in the planetary kitchen were completely different. The building blocks of its home system were not the same as ours. It wasn't just the gas, the dust was weird too. Astronomers studied the sunlight reflecting off the dust particles, a technique called polarimetry. The light came back with negative polarization, a very specific signal that we almost never see. In fact, we only see it in one place, the most ancient, untouched and primitive objects in our own solar system, the relics hiding in the Kuiper Belt far beyond Neptune. This was the final clue. The dust from 3I Atlas is ancient, fluffy and porous, unchanged since the dawn of its own solar system. This isn't just a comet, it's a pristine artifact. This is why this visitor matters so much. We call our own comets time capsules because they are frozen leftovers from the birth of our sun and planets 4.5 billion years ago. They tell us about our history. But 3i Atlas is a time capsule from another solar system. It is a message in a bottle tossed into the cosmic ocean that has washed up on our shore. For the first time, we get to read a page from the history book of an alien world. And this historic event is happening now. The visitor is on a tight schedule. On October 29th, it passed its perihelion, its closest point to the sun, surviving the fiery blast of heat and light. Now it is travelling back out away from the sun, but its path is carrying it toward us. On December 19th, it will make its closest approach to Earth. Every telescope on the planet and every satellite in orbit is being prepared. This is our one and only chance. We have these few short weeks to study it, to capture every photon, to unravel every chemical secret we can before it fades. Because after this, 3i Atlas will be gone forever. It will continue its journey, vanishing back into the interstellar night from which it came. But its brief ghostly appearance has already changed us. It is a profound physical reminder that our solar system is not an isolated island. The galaxy is a vast interconnected ocean full of other shores, other building blocks, other homes. The visitor will leave, but it leaves us with the biggest questions of all. Where did it come from? And if that is what other worlds are made of, what does that truly tell us about our own? Watching that visitor 3i Atlas fade away until it was just another speck of light, and then nothing at all, leaves a strange feeling behind. It's like standing on the beach after a mysterious foreign ship has sailed past without stopping. It just appeared on the horizon, cut across the water and vanished. You are left standing on your own shore looking out at the now empty ocean, and for the first time you start to really look at the sand beneath your feet. You start to wonder about your own harbour. That visitor made us look back at our own home. It cut right through our house, a ghost from an unknown place, and in doing so it forced us to ask, what is this house? What is this shore that it so briefly visited? We call it the solar system. When we think of the solar system, most of us picture a tidy little diagram from a school textbook. In the centre there is the sun. Then in neat, almost circular paths there are the planets Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune. We think of it as this flat spinning disk of 8 worlds and a few of their moons. But that isn't the solar system. That's just the downtown. It's the brightly lit inner courtyard. The real solar system is something entirely different. It is a bubble, a colossal, mind-bogglingly enormous sphere of influence, all centred on the gravity of our one star, the sun. The planets are just the tiny, precious jewels kept in a small box, right at the centre of a vast, dark and mostly empty kingdom. This kingdom, this bubble of the sun's power, stretches out for trillions of kilometres so far that the sun itself becomes just the brightest star in a black sky. To understand the visitor 3i Atlas, we have to understand the place it visited. We have to take a journey not to the planets we know, but to the edge of our own territory. We have to go to the deep, dark and frozen lands that lie beyond the light. Our journey starts past the orbit of Neptune. Neptune is the last of the giants, a beautiful blue world of ice and gas orbiting almost 4.5 billion kilometres from the sun. Out here, the sun is small. It's still intensely bright, far brighter than any other star, but its warmth is gone. The temperature drops to hundreds of degrees below 0 Celsius. But this is not the end. This is just the beginning of the true outer system. As we drift past Neptune, we enter a new realm. It is not empty. In fact, it's crowded. We have just entered the Kuiper Belt. Think of the Kuiper Belt as the solar system's attic, or perhaps its grand sprawling junkyard. It's a second asteroid belt, but so much larger. Where the asteroid belt between Mars and Jupiter is made mostly of rock and metal, the Kuiper Belt is made of ice and dust. It is a vast, flat ring of debris, a donut-shaped cloud of frozen relics left over from the formation of the solar system. This is the home of what we call the trans-Neptunian objects, or TNOs. These are the things beyond Neptune. And there are not just a few of them. There are hundreds of thousands of them larger than 100 kilometers across. There are likely billions, perhaps trillions of smaller ones, all silently orbiting in the deep freeze. This is the home of Pluto. For 70 years, we thought Pluto was a planet, a lonely outsider. We were wrong. Pluto wasn't alone at all. It was just the first one we found. It was the king of this newly discovered kingdom. Once we built telescopes powerful enough, we found more Eris, even more massive than Pluto. We found Makemake. We found Haumea. We found a whole civilization of icy worlds. These are the icy bodies, the planetesimal, that never quite made it. They are the building blocks that were left over. They orbit in the dark where almost nothing ever happens, and they have been there for 4.5 billion years. They are frozen time capsules holding the original unprocessed ingredients of our solar system. Now think back to our visitor to our 3i Atlas. It came into our system, and as it got closer to the sun, it started to act strangely. It started to shed dust. It began to crack and fragment. It looked like a comet. And where do many of our comets come from? The Kuiper Belt. Every now and then, the gravity of Neptune, or the slow gravitational pull of these objects on each other, gives one of them a little nudge. It gets knocked out of its stable circular orbit and begins to fall, a long, slow journey inward toward the sun. As it gets closer, the sun's heat begins to boil its ices and it grows a beautiful tail. We call this a short-period comet. 3i Atlas looked just like one of our Kuiper Belt objects. It had the same dusty, icy composition. It behaved the same way as it neared the sun. But its speed and its path told us it could not be from here. It was moving too fast. It was on a trajectory that was not bound to our sun. It was a piece of debris, yes, but it was their debris. This is the first profound realization that 3i Atlas gave us. It suggests that our Kuiper Belt is not unique. It implies that other stars in other parts of the galaxy also have their own vast reservoirs of icy junk. Other stars have their own Plutos, their own leftover building blocks. Our visitor was almost certainly a piece of another star's Kuiper Belt. It was a piece of their history, born in a different cloud of gas and dust billions of years ago. It was somehow ejected from its home system, maybe by a giant planet, and sent on an unimaginable journey, drifting through the interstellar dark for millions, perhaps hundreds of millions of years, a lonely fragment of a different home. And it just happened to pass through ours. But our solar system does not end at the Kuiper Belt. The Kuiper Belt is just the outer suburbs, the edge of the flat disk. The true border of the sun's kingdom lies much, much farther out. Let us travel farther. We leave the Kuiper Belt behind. We travel for a month, a year, a decade. We are now so far from the sun that light itself takes months to reach us. The sun has shrunk to become just a star. It is the brightest star in the sky, but it is just a point of light. It offers no heat. The planets are gone invisible, lost in the sun's distant glare. We are now in the Oort cloud. This is not a belt, this is not a disk, this is a shell. Imagine the entire solar system, the sun, the planets, the Kuiper Belt, all fitting inside a tiny seed. Now imagine a giant hollow sphere surrounding that seed, a sphere so big it stretches almost halfway to the next nearest star. That is the Oort cloud. It is the true final frontier of our solar system. It is the vast, invisible, fuzzy shell that envelops our home, and it is not empty. This is the second profound realization. This cloud is filled with the ghosts of our past. The prompt calls them Hangin Ti Sao Choi trillions of comets. This is not an exaggeration. We believe the Oort cloud is a cloud of perhaps 2 trillion icy objects, each one a mountain of frozen water, frozen carbon, dioxide and dust. We have never seen it. We cannot take a picture of it. The objects within it are tiny, black and incredibly far apart from each other. An object here might be tens of millions of kilometers from its nearest neighbor. It is the definition of emptiness. So how do we know it's there? We know it's there because it sends us messages. Every few thousand years, a magnificent new comet appears in our sky. It doesn't come from the flat plane of the solar system like the comets from the Kuiper Belt. It comes from anywhere. It can fall in from the north or from the south or from any random direction. These are the long-period comets. Comets like Hale-Bopp or Hyakutake, which stunned us with their beauty. These comets have orbits that are thousands or even millions of years long. They are falling from the Oort cloud. This is where we must pause and consider the great stillness. Let us float here in this invisible cloud. The cold is almost absolute. It is just 2 or 3 degrees above absolute zero, the lowest temperature theoretically possible. The darkness is total, broken only by the pinpricks of distant stars, one of which happens to be our sun. And the silence is defined by time. These trillions of IE comets are the original members of our solar system. They were born in the same spinning disk as Earth and Jupiter. But in the chaotic early days, the immense gravity of the giant planets Jupiter and Saturn acted like giant slingshots. They grabbed these icy bodies and threw them. They were exiled. They were thrown out of the light, out of the flat disk, and sent to this impossibly distant dark prison. And there they have waited. For 4.5 billion years, nothing happens here. 1 million years passes, the comet floats. Another 1,000,000 years, it floats. It is in a state of perfect preservation. It is a frozen sample of the original cloud of gas and dust that gave birth to our sun and our world. For billions of years, nothing happens. until one day a star passes by. Not close, but a light year or two away. The faint gravitational nudge of that passing star is just enough to disturb one of these sleeping comets. It's just enough to change its orbit. A tiny nudge, and that comet, after a 4.5 billion year sleep, begins a new journey. It begins the long, slow fall. A fall that will take perhaps 2 million years, a journey from the deep, deep dark all the way back home toward the sun. This brings us to the final beautiful comparison. When one of these comets, our comets, falls from the Oort cloud and graces our sky with a tail, we are seeing a message from our own creation. We can point our telescopes at it. We can read its chemical signature. We are analysing the very water, the very carbon, the very materials that built us. An Oort cloud comet is a letter from our own deep past. It is the story of our birth. Now think one last time about 3I Atlas. It came into our system, it looked like one of our comets, it shed dust like one of our comets. But it was not from our Oort cloud, it was not from our Kuiper belt. It was in all likelihood a piece of another star's Oort cloud, or another star's Kuiper belt. It was also a letter, but it was a letter from someone else's past. It was the story of someone else's birth. For the first time in human history, we saw a piece of another solar system, another cosmic shore with our own eyes. 3I Atlas. In its brief silent passage proved to us that our shore is not the only one. The universe is full of these shores. It is full of these vast, dark, cold reservoirs of history. The same process of creation of chaotic beginnings of exiled comets and of frozen time capsules that happened here is happening everywhere. Our home is one of many, and for a moment one of their ancient travellers washed up on our shore. For this entire journey so far, we have kept our focus small, relatively peking. We have stayed within the familiar cosmic neighbourhood of our own solar system. We've looked at the planets as our neighbours, the comets as passing visitors, and the Oort cloud as the distant fence around our property. But now I want you to pull back. Let's imagine we are in that spaceship of the mind again. We are leaving our home. We fly past the orbit of Pluto, past the Kuiper belt, past the strange icy bodies of the Oort cloud, the last frozen teardrops held by our sun's gravity. Now we are truly in interstellar space. The sun is just a bright star, but we can still pick it out. Let's keep going. We travel for years at this impossible speed. Now decades, now centuries, now thousands of years. The sun is lost. It has merged indistinguishable into a vast, glittering tapestry. We have finally travelled far enough to see the whole thing. We are floating high above, looking down, and what we see takes our breath away. It is not a random scatter of stars, it is a structure. A colossal luminous whirlpool of light hanging in the blackness, silent and magnificent. It is a flat disk with great sweeping arms, all spinning slowly around a centre that glows with the white-hot intensity of a billion suns. This is our galaxy, the Milky Way. It is our home, an island of light in the great cosmic ocean 100,000 light-years from one side to the other, and every single star you have ever seen in the night sky with your naked eye is in this structure. All of them, including our sun, are just tiny parts of this one city of stars. Let's explore our city. First, let's glide toward that brilliant dominant centre. The light becomes almost blinding. This is the galactic core. It's not a flat disk here. It's a huge, brilliant, bulging sphere of stars tens of thousands of light-years across. The stars here are packed incredibly tight, a golden swarm of ancient suns. Their orbits are frantic and fast whipped around by a truly immense gravitational pull. This is the downtown of our galaxy, crowded, chaotic and blazing with energy. But what is doing the whipping? What is at the very heart of this chaos? We can't see it directly. It's shrouded by thick clouds of gas and dust, but we know it's there. We can see the stars right at the centre orbiting nothing at incredible speeds, millions of miles per hour. They are orbiting a single invisible point of unimaginable mass. This is Sagittarius A star. It is our galaxy's supermassive black hole. Now, when we hear black hole, we think of a monster, a cosmic vacuum cleaner devouring everything. But that's not the best way to think about Sagittarius A star. It's not a predator hunting through the galaxy. It is the gravity anchor. It is the axle around which our 100,000 light-year city turns. It's more than 4 million times the mass of our sun, all crushed into a point of infinite density. Its gravity is the stabilizing force, the moneo that shepherds the stars and holds this entire beautiful structure together. Now let's pull back from that chaotic core and look at the disk itself. It's not uniform, it has those beautiful sweeping arms. These are the spiral arms. These arms are not solid structures. You can think of them as giant winding rivers, but they aren't rivers of water. They are rivers of stars, gas and cosmic dust. Or perhaps a better analogy is a traffic jam. They are density waves areas where the material in the galaxy gets temporarily crowded together. The stars and gas clouds move through the arms, slowing down as they enter and speeding up as they leave, but the arm itself remains. And this crowding is the most important thing happening in the galaxy. This is where the magic happens. As clouds of hydrogen gas drift into one of these arms, they get squeezed. Gravity takes over. The clouds collapse, fragment, and begin to heat up. This is where stars are born. The spiral arms are the stellar nurseries of the Milky Way. When you see pictures of those beautiful glowing clouds of pink and red gas nebulas like the Orion Nebula, you are looking at a star factory in one of these arms. The brilliant hot blue stars you see are often the new babies shining with intense, youthful energy. So where are we in this giant city? Are we downtown in the chaotic core? No. Are we in one of those bright, busy, star-forming arms? Not quite. We live in the suburbs. Our solar system is located in a smaller partial arm, a kind of branch off one of the main ones. It's called the Orion Spur. It's a relatively quiet, calm part of the galaxy. It's a good place to be. We are about 27,000 light-years from the core, far enough to be safe from the intense radiation and gravitational chaos of the center. We are in a peaceful, gentle current, a perfect place for a tiny blue planet to form and for life to slowly, patiently emerge and evolve over the billions of years. But the disk and the core are not the whole story. Let's float even further out high above the flat spiral plane. What we see now is a faint ghostly sphere of light that surrounds the entire galaxy. This is the galactic halo. It's not bright and defined like the arms. It's ancient, vast and diffuse, and scattered throughout it are these incredible objects. They look like little glittering snow globes, each one a perfect tight ball of stars. These are globular clusters. Each one is a gravitationally bound ball containing hundreds of thousands, sometimes millions of very, very old stars. These stars are the elders of our galaxy. They are ancient, some are over 12 billion years old. They formed when the universe was young, perhaps even before the Milky Way's disk had fully formed. If the spiral arms are the busy modern cities where new things are being born, the halo and its globular clusters are the ancient monuments. They are the old memories of our galaxy. They are cosmic fossils. The stars inside them are different from our sun. They are made almost purely of the original hydrogen and helium from the Big Bang. They hold the original secrets of our island's formation, drifting silently in the dark witnesses to its entire long history. So you see, a galaxy isn't just a static collection of stars. It's not a picture. It's a living, dynamic system. It is an ecosystem. Stars are born in the compressed gas of the spiral arms. They live for millions or billions of years. Then they die. Some, like our sun, will one day gently puff away their outer layers. Others, the massive blue stars, die in spectacular explosions called supernovas. And what happens when they die? They don't just disappear. They scatter their contents back out into the galaxy. They release all the new heavy elements they forged in their cores: carbon, oxygen, nitrogen, iron, the calcium in our bones, the iron in our blood, the oxygen we breathe. None of it was made in the Big Bang. It was all forged slowly over billions of years inside stars that lived and died before our sun was even born. This material seeds the next generation. The rivers of the spiral arms collect this recycled material and use it to build new stars, new planets, and just perhaps new life. We are quite literally the children of the stars. We are the Milky Way made conscious. And this brings us back to our interstellar visitors, like the object we call 3I Atlas. The Milky Way is our island of light. It's our home, our ecosystem, with its core, its arms, and its great cycle of recycling. But it is not the only one. Look past the halo out into the true deep blackness. That emptiness is called intergalactic space. It is a void of almost perfect nothingness. And across that void, so far away that their light takes millions or billions of years to reach us, are other lights, other points, other spirals, other islands. There are hundreds of billions of other galaxies out there. 3I Atlas was born in one of them. It was born in a different ecosystem. It formed around a different star in a different galaxy, a different island of light. And then by some chaotic event it was thrown out. It was ejected from its home and sent on an unbelievable journey as a cosmic orphan. A journey that lasted for perhaps hundreds of millions of years, flying alone through the empty intergalactic ocean. Until by pure chance it drifted into our island, our Milky Way, and passed by our sun. It is a messenger. It is a physical piece of another world that drifted to our shore. It reminds us that as vast and magnificent as our galaxy is, it is just one home among billions. The spiral arms of our Milky Way and countless galaxies just like it are not just static, beautiful swirls of light. They are dynamic, churning rivers of gas and dust. Think of them as the galaxy's grand nurseries. These arms are where the cosmic weather is most active. As they sweep through the galaxy, they compress vast cold clouds of gas. This is where the magic of creation begins. This is where stars are born. It all starts in a place called a nebula. Imagine a vast, dark and cold cloud drifting silently in space. It's mostly made of the simplest gas hydrogen with a little bit of helium left over from the Big Bang itself. This cloud can stretch for many light years, immensely large but incredibly thin. For millions of years it just floats. But deep within it, a quiet force is always at work: gravity. Gravity is patient. It gently, relentlessly pulls tiny particles of dust and gas together. As more and more material gathers in one spot, the cloud starts to collapse in on itself. Little clumps form like dense knots in a fog. One of these clumps is destined to become a star. As this clump pulls in more gas and dust, its own gravity gets stronger, allowing it to pull in even more material. It's a runaway effect. The surrounding cloud begins to spin faster and faster, like an ice skater pulling in their arms. It flattens into a spinning disk of material, and at its very center a dense hot ball of gas forms. This is a protostar, a baby star. It gets heavier and heavier as it feeds from the disk around it. The pressure at its core becomes unbelievable. As it squeezes, it gets hotter and hotter, eventually reaching millions of degrees. It's glowing now, but it's not a true star yet. It's just a very hot, compressed ball of gas. Then it reaches a magic number. The core becomes so hot and so dense, around 15 million degrees Celsius, that the hydrogen atoms, which normally push each other away, are forced to slam together with incredible violence. They fuse. They merge to become a new element, helium. This moment, this ignition, is called nuclear fusion. This is the instant the star switches on. It unleashes a tremendous self-sustaining torrent of energy. This energy in the form of light and heat pushes outward from the core. This outward push perfectly balances gravity's inward crush. The star finds a perfect equilibrium and begins to shine. A new sun is born, illuminating the darkness and clearing away the gas in its new solar system. For a star like our sun, this is the beginning of a long, stable life. It enters its main sequence, a kind of stellar adulthood. For billions of years, in our sun's case about 10 billion years in total, it will calmly and reliably fuse hydrogen into helium in its core. It becomes a dependable beacon of light and warmth. This dependable, steady output is what makes life possible. It provides the energy for planets like our Earth to develop complex chemistry. This steady breathing of the star creates a stable environment, a habitable zone, where liquid water can exist on a planet's surface and life as we know it can take root. Our entire existence, the rhythm of our days and seasons, is owed to this long, peaceful phase of our star's life. But nothing lasts forever. After billions of years, a star like our sun will run out of hydrogen fuel in its core. When this happens, the balance is broken. The outward push from fusion weakens and gravity starts to win again. The core, now mostly helium, collapses and heats up even more. It becomes hot enough to start fusing that helium into heavier things like carbon and oxygen. This new, desperate burst of energy is much more intense. It pushes the star's outer layers outward, causing it to swell up into a red giant. It becomes enormous, perhaps even swallowing its inner planets. This phase is temporary. The star isn't massive enough to keep this going. It becomes unstable. In a series of gentle puffs, it blows its outer layers of gas away into space. This expanding cloud of gas is then illuminated by the hot leftover core. The result is one of the most beautiful objects in the cosmos, a planetary nebula. It has nothing to do with planets, they just looked round and planet-like to early astronomers. It looks like a cosmic butterfly or a giant colourful eye, looking back at us, a delicate glowing ghost of the star that was. At the centre, the star's core remains. It is now a white dwarf, a super dense ember about the size of Earth but as heavy as the sun. It has no more fuel to burn. It will simply cool down over trillions of years, a diamond in the cosmic graveyard. This is a gentle, beautiful death. But what about the really big stars, the ones 8, 10 or 50 times more massive than our sun? Their lives are fast and furious. They burn through their fuel in just a few million years, and their deaths are anything but gentle. When a massive star runs out of fuel, gravity collapses the core with unstoppable, catastrophic force. It doesn't just form a white dwarf, it gets so hot and dense that it fuses heavier and heavier elements. It creates carbon, then neon, then oxygen, then silicon, building a core like an onion with different layers of fusion. It continues this process all the way up to iron. Iron is a dead end. Fusing iron doesn't release energy, it consumes it. The star's internal engine, its heart, suddenly shuts off. In less than a second, with no outward pressure to support it, the massive core collapses. The outer layers of the star with nowhere to go come crashing down onto this super-dense core and then rebound in the most powerful explosion in the universe. This is a supernova. For a few weeks, this single exploding star can outshine an entire galaxy of billions of stars. The energy is so intense that it forges all the even heavier elements, the silver, the gold, the nickel, the lead, the uranium. This violent explosion is the universe's ultimate act of creation. It blasts all these new heavy elements, the oxygen, the carbon, the iron, the gold, far out into the galaxy at incredible speeds. The star dies, but in doing so it seeds the surrounding space with the raw materials for new stars, new planets, and new life. This brings us to a profound and very personal realization. When the astronomer Carl Sagan famously said, "We are made of star stuff," he was speaking literally. Look at your hand, the calcium in your bones, the iron in your blood, the oxygen you are breathing right now. Every single one of those atoms, heavier than hydrogen or helium, was created in the fiery heart of a star that lived and died long before our sun was ever born. These elements were scattered by a supernova, drifted through space for eons as a cloud of dust and gas, and eventually gathered in a new nebula, the one that formed our sun, our Earth, and us. We are the children of the stars, we are built from their ashes. And this is where our story connects back to that mysterious traveller 3I called Atlas. That fragment of another world forged in another solar system is made of the exact same stuff. The materials that make up that icy rocky body were also cooked inside a star. Perhaps it was a different star in a different arm of the galaxy, one that died a violent supernova death and scattered its own ashes across space. Whether it's us, a rock on Earth, or an interstellar visitor from deep space, the story of our origin is the same. We are all cosmic fossils. We are all built from the remnants of these great creative fires. We are all of us stardust. We have spent our time exploring our home, our own magnificent island of light, the Milky Way. We've sailed from its bright, bustling core to the quiet, starry shores of its outer arms. It feels vast, almost infinite, a complete universe unto itself. But now it's time to pull back the camera, to zoom out further than we ever have before. We need to see that our island, as staggering as it is not alone in the dark. It is part of a much larger collection, an archipelago of galaxies floating in an ocean of unimaginable emptiness. This is the next step in our journey, venturing into that dark ocean between the galaxies. This cosmic family, our immediate neighbourhood, is called the local group. It's a relatively small cluster containing perhaps 100 galaxies in total. Most of them are small dwarf galaxies like little star-filled boats bobbing around a few huge flagships. In our local group, there are two giants, two titans that dominate all the others. One is our Milky Way, the other is our sister, the Andromeda Galaxy. Andromeda, also known as Messier 31, is the largest and most massive galaxy in our group. It is about 2.5 million light-years away from us. That number is difficult to truly grasp. It means the light we see from it tonight, that faint fuzzy patch of light you can just barely see with your naked eye on a clear dark night, left that galaxy 2.5 million years ago. That light began its journey toward Earth long before modern humans existed. When you look at Andromeda, you are looking deep, deep into the past. We call it our sister galaxy because in many ways it's our twin. It's a beautiful, massive spiral galaxy just like ours, but it's the dominant sibling. It's bigger, more sprawling, containing perhaps a full trillion stars, which is more than double the Milky Way's population. It is our cosmic rival, our neighbour, and our ultimate destined dance partner. And this is where the story takes a dramatic turn. Andromeda is not just sitting there, it is moving, and it is moving directly towards us. Every second it closes the distance by about 110 kilometres or 68 miles. It is hurtling through the intergalactic void, pulled by the relentless invisible hand of gravity, our mutual gravity, the combined pull of our two great galaxies. Now when we hear the word collision, involving two of the largest structures in the neighbourhood, our minds jump to catastrophe. We imagine a cosmic explosion of unimaginable violence, stars crashing into stars, planets being shattered and vaporized. But the reality is something far more subtle, more graceful, and unfolds on a timescale that completely defies human experience. Remember what we've learnt about the space between stars. It is almost unbelievably empty. Our nearest star, Proxima Centauri, is over 4 light-years away. Galaxies are not solid objects. They are mostly empty space populated by points of light separated by vast gulfs of nothing. So when the Milky Way and Andromeda merge, the chance of any two individual stars actually hitting each other is almost zero. This isn't a car crash, it is a dance, a slow gravitational ballet that will take billions of years to unfold. In about 4.5 billion years, our two galaxies will make their first close pass. They will fly through each other like two magnificent ghosts, but gravity will act like a powerful brake, snagging them both. They will pull apart for a time, distorted and stretched, and then inevitably fall back together again. During this cosmic tango, huge tidal streams of stars will be ripped from both galaxies, flung out into the darkness of intergalactic space to create beautiful glowing arcs, hundreds of thousands of light years long. Our solar system will almost certainly survive, but it will be thrown into a completely new orbit. The night sky for any beings who might exist on Earth billions of years from now will be utterly transformed, filled with a new brilliant tapestry of stars. After several passes over many more millions and billions of years, the two distinct spirals will lose their beautiful familiar arms. Their structures will be completely mixed, scrambled together by gravity. They will finally settle down, merging into one single gigantic new galaxy. This new galaxy won't be a spiral. It will be what astronomers call an elliptical galaxy, a massive, roundish, somewhat featureless ball of by then mostly older reddish stars. This new combined galaxy has sometimes been nicknamed Milkomeda. This grand merger, as mind-bending as it is just one event in one small corner of the cosmos. Our local group with Andromeda and the Milky Way on their collision course is not isolated. Just as we zoomed out from our island, the Milky Way, to our archipelago, the local group, we must zoom out again. When we do, we find that our local group is just one small cluster on the far-flung outskirts of a much, much larger structure. This is the Virgo supercluster. If the local group is our local neighbourhood, the Virgo supercluster is the entire sprawling nation, or continent. It is an immense collection containing over 100 galaxy groups and clusters, all bound loosely together by gravity, spanning over 100 million light-years of space. At its heart, about 50 million light-years away from us, lies the dense and massive Virgo cluster, capital city of thousands of galaxies, including the giant elliptical galaxy Messier 87, which is famous for its supermassive black hole. Our little local group is in the suburbs, and we are slowly but surely being pulled toward this massive central city. We are not in charge. We are part of a grand cosmic flow, a river of galaxies all moving toward a great gravitational attractor. But we must zoom out one final time to see the true map of the universe, the grandest picture of all. When we look at the cosmos on the largest possible scales, we see something breathtaking. The galaxies are not spread out randomly like salt sprinkled on a dark table. They are organised. They trace an enormous, intricate and beautiful pattern. It looks like a vast network or a gigantic glowing sponge, or perhaps most poetically a cosmic web. The threads of this web are called filaments. These are long twisting ropes of gas and, more importantly, dark matter. This invisible substance, which we still do not understand, makes up about 85% of all matter in the universe, and forms the invisible scaffolding for everything else. Gravity pulls normal matter, the stuff we're made of, onto these dark matter threads. And the galaxies are the dewdrops. Clinging to the web, they form along these filaments, shining brightly in the dark. The galaxies and galaxy clusters flow like rivers along these threads, all moving toward the places where the filaments cross. These intersections are the nodes of the web, the places where gravity is strongest. And that's what superclusters like our own Virgo supercluster are. They are the great, dense, bustling knots where the cosmic threads come together. But if the filaments are the everything, what about the space between them? If the universe is a web, what about the vast holes in that web? These are the voids. These are the great oceans of nothing that we referenced at the beginning. They are incomprehensibly huge bubbles of almost perfect emptiness, some stretching for hundreds of millions of light years across. While the filaments are packed with galaxies, gas and dark matter, the voids are empty. They are so empty that if our Milky Way galaxy were located deep inside one, we would look out at the night sky and see almost nothing at all. The sky would be nearly blank, with only the stars of our own galaxy to comfort us. The voids are the quietest places in the universe. There are no great mergers here. No new galaxies are being born. They are the opposite of the bustling, bright, chaotic filaments. They represent a deep, cold and profound silence. And yet they are just as important as the filaments. The universe is this beautiful, stark balance of something and nothing. The bright filaments and the dark voids. This cosmic web, this vast structure of light and shadow, is the largest pattern we can see. It is the grand stage upon which everything we have discussed, from the smallest planet to the largest supercluster, plays its part. When we stand under a clear dark sky, we are not just looking at points of light, we are looking at history. Every light in the cosmos is a postcard from the past. The light from our moon is just over 1 second old. The light from our sun is 8 minutes old. If the sun were to suddenly vanish, we would not know about it for 8 full minutes. The light from the closest star system, Alpha Centauri, is over 4 years old. We are seeing it as it was 4 years ago. The beautiful Andromeda galaxy, our nearest large neighbour, is so far away that its light has travelled for 2.5 million years to reach our eyes. We are seeing Andromeda as it was when our distant human ancestors were first walking the Earth. This means that our most powerful telescopes are not just space scopes, they are time machines. The farther we look into the universe, the deeper we look into the past. We see galaxies billions of light years away, and we are seeing them as they were billions of years ago when they were young. So what happens if we look farther, or what happens if we push our telescopes to their absolute limits, past the oldest galaxies, past the light from the very first stars? Where does this journey back in time take us? It takes us to the beginning. It takes us to the story of how all of this, the stars, the galaxies, the planets, and even lonely messengers like 3i Atlas, came to be. It takes us to the echo of creation. We call this beginning the Big Bang. It is perhaps the most famous and most misunderstood name in all of science. The name suggests a colossal explosion, like a firework detonating in the middle of a dark, empty room. But that is not what happened. It was not an explosion in space. It was the beginning of space. There was no room for it to explode in. There was no before in the way we understand it, because time itself began in that moment. Try to imagine this. All of the energy, all of the matter, and all of the space in our entire vast universe was once contained in a single point. A point of density and heat so extreme that our language and our physics break down trying to describe it. It was not a point inside anything, it was everything. And then it began to extend. The simplest way to think about it is to imagine the surface of a balloon. If you draw little dots on the balloon and then begin to inflate it all, the dots move away from each other. They are not sliding across the balloon surface. The surface itself, the fabric of space, is stretching, carrying the dots with it. This is what happened to our universe. Every part of space began to expand everywhere all at once. This is the Big Bang. It was not a flash of light in the dark, it was the moment the entire universe was filled with an unimaginable, brilliant energy. It was the birth of space, the winding of the cosmic clock. In the first tiny fractions of a second, the universe was a chaotic boiling soup of fundamental particles. It was so hot that nothing we recognize could exist. It was a plasma of quarks and electrons, a state of matter so energetic that even protons and neutrons could not hold together. But the universe was expanding, and as it expanded, it cooled. Within the first second of existence, it cooled enough for those quarks to freeze together, forming the first stable particles, protons, which are the nuclei of hydrogen and neutrons. The universe was still incredibly hot, billions of degrees, but the expansion continued. The stage was now set for the most important event of the universe's early life. Between the first and third minute, the universe entered its toddler phase. It was now cool enough for the protons and neutrons to start sticking together, but still hot enough to power fusion. This brief window of time is when the universe cooked its first ingredients. Protons fused with neutrons to create the first complex nuclei. The process was fast and frantic. By the time the universe was about 3 minutes old, the cosmic cooking show was over. The universe had expanded and cooled so much that this widespread fusion could no longer happen. And what was the result? What was the recipe the universe had made? The cosmos was now made of about 75% hydrogen nuclei and 25% helium nuclei. That's it. A vast, simple, and predictable outcome. The universe was left with a trace amount of lithium, but for all practical purposes, the universe was filled with nothing but the two simplest gases. These were the raw materials, the building blocks for everything that would ever follow. After these first few minutes, a new phase began. The universe was still incredibly hot, a few million degrees. It was a dense, glowing fog. It was not dark, but you would not have been able to see anything. The universe was filled with a plasma of the new hydrogen and helium nuclei, and a sea of free-roaming electrons. Light particles called photons could not travel. They were trapped constantly, being scattered and absorbed by the free electrons. It was like trying to see through a cloud or being inside the sun itself. The entire universe was an opaque, glowing fog. For the next 3,000 years, not much changed. The universe just kept expanding, and as it expanded, it kept cooling. It was a time of waiting. Then when the universe was 380,000 years old, it crossed a magic threshold. It cooled to a temperature of about 3,000 degrees Celsius. This was the Goldilocks temperature. It was finally cool enough for the free-roaming electrons to be captured by the hydrogen and helium nuclei. In a cosmic instant, stable neutral atoms were formed for the first time. This event changed everything. With the electrons now locked into atoms, the photons, the particles of light, were suddenly set free. The fog lifted. The universe in an instant became transparent. The light that was set free in that moment began to travel unhindered in straight lines. But here is the catch: with the fog gone, what was there to see? Nothing. There were no stars, there were no galaxies, there were no planets. There was just an enormous expanding ocean of neutral hydrogen and helium gas drifting in total darkness. This was the beginning of the cosmic dark ages. For millions and millions of years, the universe was a silent, dark, and seemingly empty place. But it was not inactive. While the universe was dark, a quiet, patient force was at work: gravity. But what happened to all that light? That first light from 380,000 years after the Big Bang that was finally set free when the fog cleared, it is still travelling. It has been travelling through the expanding universe for 13.8 billion years. And as the universe expanded, the fabric of space itself stretched, and that light stretched with it. The light that was once a brilliant, hot, visible glow has been stretched so far that it is no longer visible light. It has been stretched all the way down to the cold end of the spectrum. It has become microwaves. Today we can detect this light. It is called the cosmic microwave background, or the CMB. It is the oldest light in the universe. It is the afterglow of the Big Bang. It is the echo of creation still reverberating through all of space. When we build instruments that can see microwaves, we can look at the sky and we see it. It is coming from every direction, no matter where we look. It is a constant faint hiss of energy that fills the entire cosmos. It is the most profound discovery in human history, because it is a direct photograph of our universe when it was just an infant. We call it the baby picture of the universe. It's not a picture of the birth itself. That moment of the Big Bang is hidden from us. But this is a picture of the universe just 380,000 years later, the cosmic equivalent of a baby's first day. And this picture tells us an incredible story. It is not perfectly smooth. When we look closely, we see tiny, tiny ripples. There are spots that are minutely hotter and spots that are minutely colder. These are the ripples of density in that early cosmic fog. These tiny imperfections are the most important things in the universe. They were the seeds of everything. They were the small, slightly denser patches where gravity could get its first foothold. So we return to the Dark Ages, a vast dark universe filled with simple hydrogen and helium. And in this darkness, we have those tiny seeds from the baby picture. In those slightly denser patches of gas, gravity began to pull. Slowly, patiently, over millions of years, these clouds of gas began to draw in more and more material. They grew larger and denser. For 100 million, perhaps 200 million years, this silent work continued. And then in the hearts of the densest clouds, the pressure and temperature became so extreme that a new fire was lit. The gas ignited. The simple hydrogen atoms began to fuse together, releasing a powerful new light. Nuclear fusion, the engine of a star, had begun. The first stars were born. The cosmic dark ages were over. The universe lit up. These first stars were not like our sun. They were giants, hundreds of times more massive, burning hot and blue. They lived fast and died young, exploding in spectacular supernovae. But in their fiery cores and in those final violent explosions, they did something the Big Bang could not. They took the simple hydrogen and helium and under intense pressure forged everything else. Carbon, oxygen, nitrogen, silicon, iron. All the elements of life. All the elements that make up our world, that make up the rocky body of 3I Atlas, and that make up us. We are, in the most literal sense, the children of those first stars. We are built from their ashes, and they in turn were built from the simple gas left over from that first spectacular moment of creation. From a single point to a soup of particles to a fog of simple gas to the first stars and then to us. That is our story. That is the echo we are still hearing today. We have spent our time together travelling through the islands of light, the beautiful glowing structures that dot the cosmic sea. We've talked about stars being born and dying, about planets forming, from dust about galaxies colliding in a dance that takes 1 billion years. We've spoken of the elements forged in stellar hearts, the very atoms that make up your hand, the air you breathe, and the cold ground beneath your feet. We have told the story of what we can see, what we can touch, what we are made of. And yet all of it, every star, every galaxy, every planet, every grain of sand, every living creature, all of it is just a tiny fraction of what is really out there. We have been telling the story of just 5% of the universe. Think about that. Imagine you walked into a library containing all the knowledge of the cosmos. You spend a lifetime studying and you realize you have only read 5 pages out of a 100-page book. That is our situation. The other 95% of the book is written in an ink. We cannot see a language we do not understand. This is the great humbling and thrilling frontier of modern science. We are not just exploring a dark sea, we are realizing that the sea itself is made of something we cannot grasp. This is the story of the other 95%. This is the fabric of night. The first clue came not from what we could see, but from what we couldn't. It came from watching the things we can see behave in ways that made no sense. In the 1970s, astronomers like Vera Rubin were looking at galaxies, those beautiful spinning spirals. They were measuring how fast the stars on the outer edges were moving. Now basic physics, the same rules that keep our planets in orbit around our sun, tells you that the farther you get from the centre, the slower you should move. Stars on the far outer edge of a galaxy should be moving much, much slower than the stars near the bright dense centre where most of the stuff is. But they weren't. The stars on the outer edges were moving just as fast as the stars farther in. The galaxies were spinning impossibly fast. They were spinning so fast that if the only thing holding them together was the gravity from the stars and gas, we could see they should have torn themselves apart. They should have flung their stars out into the blackness of intergalactic space like water flying off a spinning bicycle wheel. But they weren't flying apart, they were stable. They held together perfectly. There was only one possible conclusion. Something else was there. Something invisible. Something with a lot of gravity. There had to be a huge invisible halo of stuff surrounding these galaxies, a massive sphere of matter that was holding everything together with its immense gravitational pull. We gave this stuff a name. We called it dark matter. It's dark not because it's black like soot or charcoal. It's dark because it does not seem to interact with light at all. It doesn't shine like a star. It doesn't reflect light like a planet. It doesn't even block light like a cloud of dust. Like radio waves, X-rays, they all pass right through it as if it isn't even there. It is completely, totally and utterly invisible to all our instruments. So how do we know it's there? We know it's there the same way you know the wind is there. You cannot see the wind itself, you can't reach out and grab a piece of it, but you can see the leaves on a tree tremble. You can see a flag wave. You can feel it on your skin. You see the effect of the wind on the world you can see. Dark matter is the cosmic wind. We cannot see it, but we see the galaxies it holds together. We see its gravity bending the light from distant objects, a phenomenon called gravitational lensing, like a massive invisible magnifying glass in space. We see its fingerprint in the afterglow of the Big Bang. This invisible material isn't just a small leftover part, it is the main ingredient. The calculations show that there is more than 5 times as much dark matter in the universe as there is all the normal matter, the atoms combined. This means that the beautiful galaxies we see are just the foam on the waves. They are the visible parts of the universe that have gathered and collected in the deepest gravitational pools of this vast invisible scaffolding. Dark matter is the framework of the cosmos. It's the invisible structure upon which the entire visible universe is built. We are in a very real sense living inside a ghost, and for decades we have been hunting for it. We have built detectors deep underground in old gold mines, shielded from all other cosmic rays, just waiting for a single ghost-like particle of dark matter to bump into a nucleus of an atom in our detector. So far, nothing. We don't know what it is. Is it a new kind of particle, something we call a WIMP, a weakly interacting massive particle? Is it something else entirely, something beyond our current theories we just don't know? And that is a glorious mystery. But this invisible scaffold, this dark matter, only accounts for about 25% of the universe. When we add our 5% of normal matter, we get 30%. That still leaves 70% of the cosmos completely unaccounted for, and that brings us to the single biggest, most profound and most baffling mystery of all. In the late 1990s, astronomers were trying to do something very specific. They were trying to measure the slowing down of the universe. We've known since Edwin Hubble that the universe is expanding. All the galaxies are moving away from each other. But gravity, the pull of all that matter, both normal and dark, should be acting like a brake. It should be pulling everything back together, slowing the expansion down. 2 separate teams of scientists using powerful telescopes to look at distant exploding stars called supernovae set out to measure how much it was slowing down. What they found shattered our understanding of reality. The expansion isn't slowing down at all, it's speeding up. The universe is accelerating. The galaxies are moving away from each other faster and faster and faster. This was so shocking, it was like throwing an apple into the air and watching it accelerate up into the sky, faster and faster until it disappears. It defies everything we thought we knew. Something must be counteracting gravity. Something must be pushing the universe apart. This something, this mysterious repulsive force is what we call dark energy. We have no idea what it is. It's not matter. It's not energy in any form we recognize like light or heat. It seems just to be a property of space itself. It's a cost of having space. Where there is empty space, this energy appears, and this energy has a strange anti-gravity effect. It pushes, and as the universe expands, more space is created. And as more space is created, more of this dark energy comes into being. More energy means more push. More push means a faster expansion. Faster expansion means more space, and so on. It's a runaway process. Dark matter is the pull that tries to hold the universe together. Dark energy is the push that is trying to tear it apart. And in this cosmic tug-of-war, dark energy is winning. When we do the math, this mysterious push accounts for the missing 70%. Our universe, the totality of everything, is 5% normal matter, 25% dark matter, and 70% dark energy. Let that sink in. We live in a cosmos where 95% of reality is made of two things that we cannot see and do not understand. Everything we've ever studied, every hero's journey, every war, every piece of art, every discovery, every bit of love, and every moment of sadness, it all plays out on a tiny 5% stage. The rest of the theatre is dark, and this is the final profound contemplation. We are floating in an ocean, and we have only just realized we don't know what the water is. The truth is, the universe is not only stranger than we imagine, it is stranger than we can imagine. This is not a fact that should make us feel small or lost or scared. It should do the opposite. It should fill us with a profound and quiet wonder. It means the maps are not all drawn. It means the greatest discoveries are still ahead of us. It means that a child born today could be the one who finally, for the first time, understands what dark matter is or what is pushing our universe apart. The fabric of night is not empty. It is full. It is full of questions, full of mystery, and full of a quiet power that is shaping the entire destiny of the cosmos. And we are the lucky ones. We are the part of the universe that gets to wake up, look around, and simply wonder. We have travelled so far together. We began this journey by watching a stranger, an icy guest from a distant unknown star system. We followed that speck of ice and dust 3i Atlas as it fell past our sun, a brief visitor that reminded us we are not alone. From that single visitor we spiralled outward. We looked at the vast, empty spaces between the stars. We journeyed to the very edge of the observable universe, peering back into the dawn of time itself. We have talked about the explosive birth of everything, the silent, patient dance of galaxies, and the deep, fundamental laws that write the story of creation. We have been to the edge, and now it's time to come home. Let's complete the journey. Let's travel back from the edge of the cosmos, not in a ship, but in our minds. Come back from the edge of time, back through the billions of years past, the formation of galaxies, past the birth of our own sun. Come back to this small blue planet, back to this room. Back to yourself. Just for a moment, feel the simple physical reality of your own body. Feel the air as it enters your lungs, a gentle reminder that you are connected to the world around you. And if you can just look at your own hand, it seems so simple, so familiar. You see the lines on your palm, the shape of your fingers, but what are you really looking at? This hand is made of materials. It is built from trillions of tiny atoms. Let's pick just one of them. The carbon atom, the very atom that forms the backbone of all life on this planet. Every single particle of carbon in your hand, in your heart, in your brain was not made here. It was not created on Earth. It was forged billions of years ago inside the heart of a dying star. Imagine a star much larger than our sun coming to the end of its life. In its final magnificent moments, it exploded in a brilliant flash of light, a supernova. In that incredible furnace, hotter than anything we can imagine, simple atoms were crushed together to create new heavier elements. It created carbon, it created oxygen, it created iron. That star's death was a creative act. It scattered its ashes, this new precious stardust, across the galaxy. That dust drifted for millions, perhaps billions of years. It swirled into a new cloud of gas and dust, a cloud that would one day collapse to form our sun and our Earth. And that carbon born in a stellar explosion eventually became part of this planet. It was taken up by ancient oceans, by plants, and now it is part of you. You are quite literally holding the remnants of a long-dead star in your palm. Now think about another atom. Hydrogen, the lightest and most common element in the universe. The hydrogen atoms in your body, the H in the H2O. The water that makes up most of you are even more ancient. They were not made in a star. They were made in the first few minutes after the Big Bang itself. These atoms are almost 14 billion years old. They are the original material of creation. They have been present for the entire history of the cosmos. For a brief fleeting moment, these ancient particles have come together to form you. They are borrowing your consciousness to look out at the world. We have a powerful feeling that we are separate. We feel like we are in the universe. We feel like we are a person on a planet looking out at the stars, but this is a beautiful illusion. The atoms themselves tell us the truth. The boundary between you and the rest of the cosmos is not a solid wall. It's more like an open door. You are not just in the universe, you are the universe. You are a temporary, intricate, self-aware pattern. You are the cosmos becoming conscious. You are the universe's way of thinking about itself. The curiosity you feel when you look at the stars, that is the universe being curious about itself. The awe you feel, that is the universe appreciating its own profound beauty. Let's think back to our icy guest 3i Atlas. We saw it as a lonely wanderer, a traveller from another star system just passing through. But is it so different from you? It is a collection of ice and dust bound together by the laws of gravity and chemistry following a path set by physics. It is a temporary expression of the same cosmic laws that made you. You are a collection of carbon and water bound together by the laws of gravity and chemistry following a path through time. You are also a traveller. You are a traveller on this planet just as 3i Atlas is a traveller through the solar system. One is a comet, one is a consciousness. Both are temporary beautiful expressions of the same universe. Both are just stardust animated for a little while. So the next time you are outside on a clear night and you look up at that vast dark sky, I want you to change your perspective. You are not small, you are not just looking out, you are looking home. When you see the pinpricks of light from distant stars, you are seeing your own history. You are looking at the stellar furnaces that created the very elements that make you. You are seeing your deep ancestral past. When you look at the wide milky band of our galaxy splashed across the sky, you are not seeing something distant. You're seeing the city of stars you live in. You're on a small blue speck swirling in the beautiful spiral arm of this grand structure. And when you look into the dark spaces between the stars, you are seeing the future. That is the cosmic dust and gas from which new stars, new planets, and perhaps one day new life will be born. The atoms that are you for this short time will one day return to that darkness to be recycled to become part of something new. You are not separate from this. You are part of a grand, unending cycle. You are as much a part of the night sky as the moon or the stars. We have travelled so far tonight from the edge of creation all the way back to our own hands. It is a lot to hold, but for now the journey is over. It is time to rest. As you close your eyes, feel the gentle, constant pull of the gravity. That is the Earth holding you. It is the sun holding the Earth. It is the centre of our Milky Way holding the sun. You are not lost in a void. You are being held, you are secure, you are exactly where you're supposed to be. So let the questions fade, let the wonders settle, let the journey come to a gentle close. You are made of stardust, you are a child of the cosmos, and you are floating safe and sound in the arms of the Milky Way. Rest now. Good night.